So these are your basic forms that are what you're going to use L'Hopital's rule for. When you have 0 over 0 or infinity over infinity, then you're going to try and use L'Hopital's rule. But there's other indeterminate forms. Now, to use L'Hopital's rule, you're still going to have to manipulate things to make it look like this. So 0 over 0 or infinity over infinity. Those other indeterminate forms are kind of fun to ponder. 1 to the infinity power. I mean, 1 to any power is 1, but infinity, I don't know, who wins? Or what about 0 to the 0 power? Wow, what's that one? How about infinity, but to the 0 power? Is that 1? Or how about 0 times infinity? 2 titans, what wins? And of course, infinity minus infinity. So there's a lot of different forms of this that you can work with that if you manipulate it in this form, then you can use L'Hopital's rule. But these are all interesting problems, and we'll do a couple. Try and give you a flavor of what you can see here. And actually, what will come out of this is a familiar limit, one that you saw first in intermediate algebra, or at the very least, college algebra. And we'll start with problem number 46. So the limit as x approaches negative infinity of x times the ln of 1 minus 1 over x. Ooh, wow. So if you were to think of this, you start thinking about, gosh, where's that going? Well, let's think of it in 2 parts. On the one hand, you've got this part out front. So that's going to be a negative infinity. On the other hand, you've got the log of this. And what happens when we put in negative infinity? What happens to that 1 over x term as I put in negative infinity?
Goes to 0.
Goes to 0. So basically I end up with the log of 1. Can anyone tell me what the log of 1 is?
0.
0. 0. So wow, what wins? This is like the clash of the titans here. So I want to use L'Hopital's rule, but in this current form, I can't. I don't have 0 over 0 or infinity over infinity. So I'm going to play a little trick on my problem. I'm going to rewrite the limit as x approaches negative infinity, ln of 1 minus 1 over x divided by 1 over x. Now, can you see what I've done? I'm dividing this by the reciprocal. If you invert and multiply, that'd be like multiplying by x. So these 2 things are equivalent, but rewriting it like this, now as I approach infinity, well, I'll have a 0 here and a 0 here. Actually, as I approach negative infinity, but it still means the same thing here for us. Both of those are going towards 0. So I can use L'Hopital's rule now. I just got to be careful that I differentiate the numerator here and the denominator here. That's my numerator denominator for this reworked version of problem 46. So are we okay with my little trickery here? This tells me, okay, yeah, I can maybe do something if I can put it in the right form. This tells me I can use L'Hopital's rule. It used to be an extra credit question for my students to correctly spell with all the punctuation L'Hopital's rule in the test. But as much as you're at home, you can Google this. Might not be an extra credit question. We'll have to come up with something else. Let's find some derivatives here. As far as finding the derivatives is concerned, let me do this part over here. D by dx of 1 over x is really the derivative of x negative first. And what happens here? Well, that's negative x to the negative second, or negative 1 over x squared. So it's just a handy side calculation to have, is that one right there. Let me put that in a little box. Because I'm going to use L'Hopital's rule, I'm going to get the derivative of the denominator. Limit as...
I pulled up some videos for you.
Wow. How do I shut that off? Could you guys hear that? That
I
was
think it
weird.
just accidentally turned on.
Unfortunately.
Man. Next thing I know, it's going to be saying, hey, do you want me to surf over to Tinder for you? Or something embarrassing like that. All right. So let's see. That's going to be negative 1 over x squared. And now I need to differentiate this. So the derivative of the natural log function is going to be 1 over that function times the derivative of the inside. Now for the derivative of the inside, derivative of 1 is going to be what? Derivative of 1 is going to be 0. So then all I'm left doing is differentiating negative 1 over x. Well, I kind of already got that. The negative and the negative are going to cancel. It's going to leave me with 1 over x squared. So
Why aren't you using the division rule here?
What
The
is that?
quotient rule to find the derivative of the equation or the function.
Well, because you got to remember, L'Hopital's rule says you differentiate the numerator and differentiate the denominator. So I'm not applying the quotient rule. I'm not trying to find the derivative of the whole function, in which case you'd be right. I'd have to be using the quotient rule. L'Hopital's rule says you differentiate the
separate.
numerator and differentiate the denominator. Yeah. Let me pull back up the actual rule here. Maybe see if I can't zoom in a little bit. But yeah, so you've got a quotient here, f of x over g of x. You differentiate the numerator and differentiate the denominator, but you're not applying the quotient rule itself. This would be nice if the quotient rule was like this. More people would do A work on their calculus class, but you're just differentiating the numerator and differentiating the denominator. Does that help?
Yeah.
Thank you. Okay, so we got good news here. Can anyone see the good news? Before I get all mired in calculations, let me make my life easier. What makes my life easier here?
Multiplying by negative x squared.
Can you cancel out the denominator with that 1x squared and leave the negative?
Yeah, so
Yeah.
what you suggested, I think Ron maybe suggested that would work, but I want to go for the easy part. Let's just cancel out that and that right away, right?
Mm-hmm.
What do you do with the negative? Because it's not the
Well,
exact.
let me just put that negative up top. How about
Okay.
that? So negative 1 over 1 minus 1 over x. How's that looking? Well, that one I can do. Tell you what, I'll do the limit in the numerator. As x approaches negative infinity, well, that stays negative 1. How about the denominator? As x approaches negative infinity, that's still a 1. But what happens to this term?
Goes to 0.
Thank you. Goes to 0. So just get negative 1. Not bad. Not bad. So a little bit of trickiness because we had to rewrite the expression at the beginning. We had to rewrite it because we wanted to get it in L'Hopital rule form. 0 over 0. But after that, a little care with the derivatives, take the limit, we're done. Goes to -1. Let me see if I got that one graphed on my link. So any question before I switch screens here? All right, let's go back here. And that's cool. Got that one there. Oh, but the limit is not as x approaches 0. Remember, the limit is as x approaches -infinity. And as you get farther and farther out the x-axis in the negative direction, you're going to get closer and closer to -1. So let me kind of zoom out this way. And if you wanted to, you could add in the line y equals -1 to your graph and see that this is getting indeed very, very close to that limit of -1. Beautiful. It's nice to see that what we're seeing graphically matches what we did with our calculations. Without ever having looked at the graph, we ended up with -1. Okay. Comments on 46. Let's try problem number 60-ish.
What does it mean when you say ish? Is it because like we're not doing the full problem?
It means I changed something in it, usually something small.
Oh,
So
I see.
let me take a look at problem 60 as it's written in the book. So you can look at this in the actual book. But yeah, in the actual book, they've got a little bit more going on here. So we're going to take a look at the limit as x approaches infinity of 1 plus a over x to the x power. Well, that's kind of strange. Now, in the book, they've got a b times x here, and that makes it a little bit more annoying. I want to keep this a little bit friendlier. Now, can anyone tell me which indeterminate form we're looking at here? I gave you several. I'm going to remind you of that list. Here's that list. Which indeterminate form are we looking at? Well, play some games mentally. If you plug in infinity, a is a constant. So as x approaches infinity, what does this go to?
Is it
0.
That goes to 0. Good. So you'd have 0 plus 1. Basically, you have 1 in here. So the x power. So which
1 plus infinity? Or
1 to the infinity? Yeah, 1 to the infinity power. That's exactly what this is looking like. It's like, oh my gosh, what a mess. So, all right, well, let's see if we can't figure out what this limit is. But you're right, it's 1 to the infinity power, and that's a little bit of a problem for us. So here's what we're going to do. I'm going to give that limit a name. I'm going to call y equals the limit as x approaches infinity of 1 plus a over x to the x power. And if you notice, I left myself some room in front of that ln term. So I'll play a little trick here. Here's my trick. I'm going to take the natural log on both sides. Why? Well, it's going to help me out. On the left-hand side, I'm just going to leave that as ln of y. On the right-hand side, I'm going to interchange limit and the log. I can do that because this is a continuous function. So far, it looks messier and it doesn't look like I've gotten anywhere. But I'm actually pretty close to the point that I really need. So what's going to happen here? What do you think I can do next?
The X can come down.
Thank you. We're going to use our properties for logs. The X can come out in front, X ln of 1 plus A over X, like that. And this is again an indeterminate form. I've gone from 1 to the infinity to infinity times 0. So it's still indeterminate, but can I apply L'Hopital's rule yet? No, can't apply L'Hopital's rule yet. But at this point, you have seen a trick that does work for us. What works? What do you think I can do here? We did it in our previous one.
Find the derivative.
I can't. Good try. I can't differentiate this yet because it's infinity times 0. It's an indeterminate form, but it's not in L'Hopital rule form. So,
A over X.
say again?
Divided by A over X.
Nice. That X, multiplying by X is the same thing as dividing by 1 over X. And that's the step that I really needed here. This finally turns it into a 0 over 0 proposition when I apply L'Hopital's rule. And I'm thinking of two functions. Thinking of the one in parentheses in the numerator and the one in parentheses in the denominator. Those are two separate functions, both of them going towards 0. That is L'Hopital's rule. So when I differentiate, limit as X approaches infinity, I'm going to differentiate the numerator and differentiate the denominator. We just did a problem in which we calculated the derivative of the denominator. We got -1 over X squared. In the numerator, the derivative of a log function is 1 over the function times the derivative of the function. A derivative of 1 is 0. Derivative of A over X is going to be -A over X squared. Okay. Does this simplify at all? Actually, yes. Negative and a negative cancel, so I can get rid of those. So I can get rid of those. What else cancels? Very obligingly.
1 over X squared.
Yeah, the 1 over X squares. So let me get rid of the X squares. Well done. So what I'm left with, ln of y equals the limit as X approaches infinity of, well, it's just going to be A over 1 plus a over x. So what happens here? Limit as x approaches infinity, a is a constant, 1's a constant. What happens to a over x?
It's 0.
So overall, I get this limit is a. You see one problem though. Limit is 8, that's right, that's great. There is one tiny little glitch though. A is the limit of the log of all this. A is the limit of the log of y. If I wanted to actually find y, the limit, how would I get y by itself? What would I have to do?
Divide it
No, not quite divide it.
or multiply it. Multiply ln.
I appreciate the effort.
Is it 1 over y? Oh, never mind.
You have to exponentiate both sides. So basically you would do this. You would do e to this power equals e to that power. These two operations are going to cancel each other out. E to the ln of y cancels. So it's going to leave you with y equals e to the a. Whew. Don't worry. I usually put less than 5 or 6 of these on an exam. No one's laughing. All right. Maybe if they
I mean,
do-
I'm hoping that you're joking.
All right, nervous laughter then. No, I certainly wouldn't put that many. For one thing, it would be a real bummer to grade, but no, wouldn't put that many. You should probably expect at least one where you have to manipulate things to put them in an indeterminate form. So we've done a couple here at the end here. So, but it'd be no more than one. Another thing you can expect, that's something we did a couple of them for, is having to apply L'Hopital's rule multiple times before you get down to an answer. I mean, that's reasonable. But no, there's only so much of that I want to put on an exam. What do you think about L'Hopital's rule? Pretty cool.
So for example, if we were to do a limit problem, we can either just plug in the limit if it doesn't happen to be in the like 0 over 0 or infinity over infinity form, but if it does, then we can just use the L'Hopital rule.
Yeah, so you want to use L'Hopital's rule when you can and when it's convenient and appropriate, but you don't always have to. I mean, I think we started this section out by doing one in 2 different ways. It was this one right here. When we did this one, I said, hey, look, you can factor it and do it that way. There's nothing wrong with doing it that way. The fact that we ended up doing it with L'Hopital's rule was fine. But I mean, L'Hopital's rule for this problem is like squirrel hunting with a bazooka. It's overkill, right? It works. I mean, there's nothing wrong with it, but yeah. If you can do it by an easier method, go ahead. I'm not going to make you use L'Hopital's rule. You're going to end up using L'Hopital's rule because you have to, not because you necessarily want to. I mean, sometimes you can use it just to be lazy, easy, and there's nothing wrong with that, especially if you're using it correctly. Sometimes you're going to have to use it, and I would expect that you're going to have to use it at least once on the exam.
All right, thank you.
Mm-hmm. So the only like, what were they called? Indeterminate forms that you can use L'Hopital's rule with is 0 and 0, 0 over 0, and infinity over infinity, right?
Yeah. Now with
So the other
infinity
ones
over
don't
infinity,
count.
infinity over infinity, it's really plus or minus, and you know the book doesn't really write it, but it could be plus or minus infinity over plus or minus infinity. Doesn't matter if it's going to infinity or negative infinity. The signs don't matter. If it's infinity over infinity in some form, then yeah, you can use L'Hopital's rule. The other ones are indeterminate forms, but you can't use L'Hopital's rule until you put it into one of those forms. So these are a lot of indeterminate forms, but it's only when you get here that you can finally use L'Hopital's rule. You want one more example from L'Hopital's rule? Going once, twice. All right, good deal. That'd be page 10. Whew. All right. Now, I think I sent you an email that had an attachment on it talking about, you know, ways to graph things in calculus. And the book has one as well. Oops, actually, that's wrong. Class, let me take a look here at our D2L site. Should be on one of the handouts. Yeah, here it goes. Graphing with calculus guidelines. So when you're doing problems for WebAssign, this is kind of what it expects. It expects you to look at the domain of a function, look at its intercepts, any symmetry, asymptotes. And the nice thing for us is that L'Hopital's rule really lets us investigate any asymptotes pretty nicely. So what happens when the function is approaching, or is that as x approaches infinity? What happens to the function? Or are there vertical asymptotes? Our derivatives help us find intervals where it's increasing or decreasing, local minimum, local maximum values. The second derivative helps us find concavity. And then all this information can be pulled together to draw a nice sketch. Now, the challenge for me is that, well, you've got Desmos, you've got a graphing calculator. There's beautiful things out there to help you try and graph these things. The question is, you know, what am I going to do on a test? And I want to try and answer that this evening. But first, let's try and take a look at a problem from section 4.5 and, you know, go through a few things about this. So we're moving into section 4.5 right here. Now, the handout that I sent you is my version of what's online on D2L from the book, which is basically graphing with calculus, and it pretty much says most of the same things. So let's take a look at section 4.5, starting with problem number 4. So y equals x to the 4th minus 8x squared plus 8. They want you to graph this, and let's just go through all the little steps. I mean, look, you can come up with a graph really easy, and that's fine, but I'm going to want you to find significant points. So, in fact, let's take a look at the graph after we decide the domain and something else about this function. Domain should be the easy part. What's the domain of this function?
Negative infinity to infinity, all reals.
Thank you. Negative infinity to infinity, or better yet, all reals. Script R. Beautiful. There's something else that catches my eye about this function. Can anyone just look at that and go, oh, yeah, okay, I see it. It's
It's missing a term.
it's an even function. And that actually has an importance. Does anyone know what the characteristic of an even function is? I mean, not just even exponents, because cosine is an even function, but it doesn't have any exponents. This one's an even function, and the technical definition of that is f of x equals f of negative x. That's how you
Symmetrical?
check it. Yeah, it's symmetric with respect to the y-axis. So that's the important thing here, is that it's symmetric with respect to the y-axis. And that's nice. It's a good feature to know about a graph, is that it's a mirror image of itself across the line x equals 0, which is the y-axis. So here's our graph. It's on one of the links I sent you. And like always, I'm gonna go up here and hit the projector button, projector mode. And that's good. Then you can see we got some minimums. And Decimals is pretty nice because it finds some minimums for you. But I think you'd be hard pressed to find where it changes concavity. Now don't get fooled. This is the x-intercepts of these graphs. It's not where it changes concavity. It's tough to look at this and say, oh yeah, right here or right here. I don't know. So let's work with this and see what we can find. We'll start out with the first derivative. Y prime, of course, would be 4x cubed minus 16x. And we can factor that. That'd be a 4x times x squared minus 4, which further factors as x minus 2 times x plus 2. And okay, that's good. But what does that tell us? What's that going to tell us here? Well, if I knew where it's 0, that might be something interesting. Can anyone tell me where it equals 0? What values of x?
0, 2, and negative 2.
Perfect. 0, 2, and negative 2. 0, 2, and negative 2. So those three places. Those are our critical points. So interesting things should be happening at the function at those points. Now this might be overkill for this one because we can just look at the graph and kind of tell here what's going on. Let's just see that it works. X, y, and y prime. I've got points at negative 2, 0, and 2. Make sure you list those in order. If you list them in opposite order, it could really mess you up, be misleading. All right. Yeah. All right. Just gonna have to do it the old-fashioned way. There. There. Okay. So let's see. The derivative is 0 at all these places. Might not be a bad idea to actually find the y coordinates at these points. You could do that by substituting in up here. But then you can play a game of testing points in between to try and find out the sign of these derivatives. And let's see. Let me save us some time with our calculator. Let's see. I think that's going to be positive, negative, positive, negative. Let's just double check it with the graph. Does that work? Yeah. So up until the point negative 2, the graph is decreasing. Between -2 and 0, the graph is increasing, then decreasing, and then increasing again. So yeah, 4 intervals. We get a nice match. Decreasing, increasing, decreasing, increasing. Just what I was looking for. But let's go back up to our graph here, or our first derivative. What's the second derivative going to be? No one?
12x minus 16.
Thank you. 12x squared minus 16. And kind of like the last one, I want to know where that's 0. So if I solve, I'll get x squared equals 16 divided by 12. And take the square root on both sides, x equals plus or minus. Square root of 16 is 4. Square root of 12, that'd be 2 square roots of 3. So plus or minus 2 over the square root of 3. And I don't care if you rationalize it. You know, in fact, don't worry about it. I want you to worry about the calculus, not the arithmetic here. So let's do some more testing of points, x, y, and y double prime. We've got two values, -2 over root 3 and 2 over root 3. Second derivative is 0 at both of these places. Here. 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 Now our second derivative function, let me write it up here again, is 12x squared minus 16. So let's see if we can't test some points without necessarily taking out a graphing calculator to do that. We're going to test them up here. So I suppose I can get away with -2, 0, and 2. So 2 squared will be 4 times 12 minus 16. That's going to be positive. Putting in a 0 here, that's going to be negative. These two are going to be symmetric, so that one's going to be positive. But that's good to know. That tells me some nice stuff about my graph. Tells me that the function is doing what here in this interval? What's its shape?
Concave up.
Concave up. Cool. Thanks, Lena. Glad someone's with me. And then in the middle one, concave down, concave up. Does that match? Does that match what we see? Well, at least it looks symmetric. And we expect our graph to be symmetric because it's an even function. But let's see what that graph is. That's right here. I've taken the liberty of putting those points on our graph here for us. All you have to do is click these dots, put them there, and there you go. So this is actually where our function changes concavity, not at the intercept, but right here, a little bit removed from the intercept. Not a spot that I'd be able to put my finger on and say, oh yeah, right here. I mean, it looks close. I probably would have guessed something in between here somewhere, but yeah, maybe it's happening a little earlier than I would have expected. In any case, these are the points that I would ask you for. Where's the concavity change? By the way, what does that mean I can label these points as?
Inflection points.
Nice, inflection points. And I'm just going to get lazy over here, IP. This also gives us some information. That's going to be a local, what? Decreasing, then increasing. This has to be a local
in
min, local max, local min. Nice. All right. So I think we nailed that one. I think we got all the good stuff out of this one we're going to get. So got a couple more here that I want to work on. And we're going to do something a little bit different, a little bit fun here. Are there any comments on this one? Problem number 4. To see how all the things we brought together in all our math courses, domain, even function, derivatives, second derivatives, inflection points, all those things are coming together to help paint a really solid picture of what that graph looks like. I mean, a picture's worth 1,000 words, and it's nice that we can graph it on our graphing calculator or Desmos, but what those technologies won't find for you is what we found, and that is things like the inflection points here and here. So, anything else about this? Let me remind you, in contrast to this, about an odd function. So, I think I can get rid of this.
I'm sorry, but for the points that you found in the graph, how exactly did you know it was going to be there? Because I know we have the x coordinate for that, but how did you find the y coordinate?
Great question. You got to put those back into the function to find the y coordinate. So, for instance, if I wanted to know, say, this point right here, I'd have to put it back into the function for y. So let's take a look at that. That'd be y equals -2 over the square root of 3 to the 4th power minus 8 times 2, -2 over square root of 3 squared plus 8. So that's going to be 16 over 9 minus 8 times 4 over 3 plus 8. And let's just let our calculator do the work from here. In fact, you can let your calculator do your work much earlier than this. 16 divided by 9 minus 32 over 3 plus 8. And if I hit the answer to fraction key, I end up with -8/9, which I think and hope is what I put on our graph here. Yeah, -8/9. Okay?
Yep. All right. Thank you.
Yeah. Now let's cheat on something. So we got the 1 point here at, let's say, no, actually, I guess I put in this one. I put in this one here, but because this is an even function, I know I have a symmetric point over here. So that means I kind of get this one for free. And that's the advantage of knowing that you have an even function, is that, okay, you know, one of them is going to be x and some number, the other one's going to be -x and the same number. So that's nice if you have an even function.
All right. Thank you.
Thanks for the question. So it's harder to recognize an odd function. There's a place later in the course where it's really handy to recognize things that are odd functions. So let me help you out with that. For instance, y equals, let's do 3 sine of x. This is going to be an odd function. And it's not very striking that this is an odd function. So what defines an odd function, if you just want to look at it on its graph, is that an odd function has what's called origin symmetry. If I draw a line, any line, through the origin, so it's going through 0, 0, that line is going to strike the graph at opposite sides of the origin. So 2.279 in this, and then, oh, I got the exact negative point of that. And if I move this line a little bit, it's still going to happen. So let me move over to here. So I got this point here, and I'm going to have a symmetric point over here. And likewise here. So it's not easy to see visually, but if you rotated that line around, you're going to have points that are on opposite sides of the origin. So for instance, you got one here at pi and 0. There's going to be another one over here at negative pi and 0. That kind of thing. So I want you to try and experience some of the ways I can ask a problem like this on an exam. If you happen to have that link that I emailed you, or if you're on Desmos, then open up mystery function. Yay. So we're going to look at mystery function number 1. And then maybe we'll take a break. But for mystery function number 1, let me give you some clues. Blue's Clues, right? Some of you should know that one. No one's admitting anything. I know. It's all right. Your secret's safe with me. All right. Let me go back to this. I think this is actually on an attachment that I sent to you by email. So if you don't want to copy it down in your notes directly, that's fine. But there's a lot of information I'm going to give you about this graph. And what I want you to do is see if you can't put this stuff together to try and form a picture in your mind of what the graph would look like. And what I do here on this link is I ask you, questions, and then you can hit the circle to try and see if you're right, because the circles are going to reveal the right answer. And what I'll do here is I'll put you into groups so you guys can work on this together. And then we'll come back and I'll go over what you should have gotten out of this. So let's see. I'll put the link here. Oops. I hope I grabbed that right one. Let's see. Yeah. I'm going to put the link in the chat in case you haven't gotten it another way. There you go.
What about those of us that are on phones?
That's a good question. I don't know. I'll keep my screen here, and hopefully you can talk with your companions about some of the things you should be able to deduce based on this. But this gives you a lot of information. I told you the domain of the function. I told you that's an odd function, and then f of 2 equals 0. I gave you some information about the derivative and the second derivative. And actually, here, let me squeeze it out. There you go. So hopefully together you can certainly talk through a lot of the details about what this graph should look like. You might miss out a little bit on the fun of, the big reveal, but, do your best. So with all this information, we should be able to fill out some of the questions here. Now our domain is -2 to 2, and we've got an odd function who's got a point at 2 and 0. Now because it's an odd function, if we had a 2 and 0, where's our other point? Well, it's symmetric with respect to the origin, so that would put it probably there, right? -2. So good. Next thing, where are the critical points? Well, how do you get a critical point? Somebody help me out here. What are the critical points?
If the first derivative is equal to 0 or does not exist.
Good. So the first derivative is 0 or does not exist. Now, here's a couple gimmies, right? The first derivative is 0 at both of these points. But there's actually the first derivative. Is there a place where this doesn't exist? Is there a value of x that makes that fraction undefined?
Well, 2.
Yeah,
A
2.
-2.
2 or -2. So both of those. So overall, in terms of critical points, you should have 2, -2, -√2, and +√2. So all 4 of those should be lighted up when we click this next circle. And let me zoom out a little bit. There we go. But there you go. There's all 4 points. So, and in particular, we know something special about a couple of these points. This one right here, for instance. And let's look back at our graph or a little chart here. The derivative is negative to the left of this and then positive to the right of this. So what's that tell me about this point? That's a local minimum. And this point's going to be a local maximum. But as far as increasing and decreasing, well, let's take a look back here. They want to know where is the function increasing? Can anyone tell me where the function's increasing? Come on, somebody help me out so we can go on break.
Between -√2 and +√2.
Perfect. Between these two, where the first derivative is positive. And when you click here, bam. Oh, that's beautiful. Between -√2 and +√2. All right. Where's the function decreasing? Well, it's kind of got to be decreasing outside of that, right? And you can look back at our first derivative and see it's increasing where the graph is red, and it's increasing or decreasing where it's red and increasing where it's blue. Now, there was one last question here. Actually, maybe a couple last questions. It says, does the function have an inflection point? What would be true if the function had an inflection point?
It goes from positive to negative in the third derivative or the second derivative.
Yeah. So the second derivative changes sign, either from positive to negative or negative to positive. But there's a change in sign, and so that change in sign happens at 0. So, yay. Let's see if we can't highlight that one. Bam. That's where the function changes concavity. Probably where you would have guessed it to be, but we saw in the last problem that it's not always where you might think it is, so it's nice to have the calculus to back us up. Okay. And this is your odd function. Let me remind you of that kind of symmetry here by taking this line and zooming it around. Notice that on opposite sides of the origin, you have symmetrically located points here and here, for instance. So nice. All right, we're going to do one more like this. The difference is in the next one, I'm actually going to give you the function, but I'm again going to ask you questions and different questions. So here's the function, here's the first derivative, here's the second derivative. So if we want to copy that down, that's great. We're going to use the time after the break to see if we can't figure out some stuff about that function. And I'll send the link to you right now through the chat if you haven't opened it up elsewhere somehow. I'll take a break. I'll see you in 6 minutes.